Hello. In this lecture, we are going to discuss about spatial analysis with vector data. With the help of vector-based geoprocessing tools, we can able to capture, integrate, manipulate, analyze, and display geospatial data, which includes overlay analysis, using which you can edit the geometry of your layers. You can perform spatial query based on attribute information and geometrical information, especially spatial relationship between the features. And you can create new data with the tools like proximity analysis or overlay analysis. Say, for example, buffer tool, where you can create zone of interest around a point of interest. And even you can compare multiple layers, and you can subset the layers based on other layers, and you can extract values and you can analyze. In addition, vector-based tools also offer specialized analysis like a spatial statistics, where you can apply mathematics and statistics for locational data, using which you can identify the patterns, clusters, outliers, and etc., trends, etc. You can do a network analysis with the network data sets and network based tool sets, where you can able to find the shortest path, origin destination, cost benefit analysis, location matrix you can perform. And even you can convert your point data into continuous surface using interpolation tools, where you can predict the values for unknown locations based on the known location values. You can do suitability analysis by integrating multiple layers with different vector based tools, where you can build a complex models in order to perform suitability analysis. For vector analysis, geoprocessing tools are required, which are offered by GIS software, and the most widely used software ArcGIS and QGIS offer hundreds of vector-based tools for various analysis. Both the softwares offer similar interfaces, and many of the tools, geoprocessing tools, looks each other. And one advantage of ArcGIS is ArcGIS provide comprehensive support, where you can access online modules, tutorials, and their rich documentation, which are all not much possible from QGIS, because QGIS tools mostly developed by the community users, so their documentation is sometimes inconsistent. ArcGIS offers a variety of toolboxes that contain tools, and all the tools are arranged in a logical manner under different headings, and those like headings we call it as a toolbox. So you can find hundreds of tools with this geoprocessing toolbox. And some of the tools are widely used, say for example, spatial analysis tools, 3D analysis tools, network analysis tools, so geostatistical analysis tools. These tool sets are widely used for various vector-based applications. QGIS also offers many vector-based geoprocessing tools, and one advantage of QGIS is it offers extensible plugin architecture, where you can connect external libraries into QGIS, and you can create your own tools, and you can perform many geoprocessing. And those vector analysis tools of QGIS, some of them are powerful, which may not be like possible to do it with the other softwares. Let us look some common vector-based analysis in upcoming slides. Sometimes you may not have a data set for performing vector-based analysis for which you have to create futures. Sometimes you may have a futures, but that may not suit for your analysis where you have to edit it. ArcGIS and QGIS, even other GIS softwares offer many tools to capture the data. Even nowadays, you can connect online imagery or other data sources where you can look at different information and you can collect those information in form of layers. Using those layers, you can do many vector-based analysis. One of the most fundamental and powerful vector-based analysis is the spatial queries. Spatial queries allows you to search for features based on its spatial relationship with its geometry as well as the spatial relationship between the geometries. It is similar to traditional SQL queries, structured query language queries, but the difference is it performs based on the locational information, especially the distance. Say, for example, you are searching a hotel or restaurant nearby your location in your Google Map or similar app. You could able to list of hotels near you because at the back end those apps will apply this spatial query based on the distance from your location and pop up. Sometimes you can refine those informations based on the distance and you can limit within 1 kilometer or within 1 mile. So what are the like hotels or restaurants available? And you can able to the filtered information based on this spatial approach. So almost most of the online mapping applications provide the spatial queries directly or indirectly, and most of them are doing it at their back end. Buffer is one of the fundamental tools in GIS. Even for spatial query, also buffer normally used. It creates a polygon around a feature of interest at a user provided distance. So with the help of your future, you can create a zone of interest around your future. Either it can be a point or line or even area. You can create a buffer around, and those buffer sometimes are helpful to extract meaningful information and do or perform some analysis. Another very interesting and important tool set is overlay tool set. There are many overlay tools available in GIS software. Say, for example, you have two layers, and one layer it's wider, and another layer it's smaller area, and you want to extract the information from the wider feature using the smaller like entity. You can use the clip feature in which it will clip only the part you are interested and it will create an output. In opposite, you can do also arrays where within your input a certain part you want to remove it, and using arrays feature you can remove it and you can extract only the portions falling outside the arrays features. Even you can compute a geometric intersection based on input features. Say, for example, here two features given together, the common area of both the features will be extracted. We call it as intersect, and the features that overlap in all layers will be written as output. Like you can do many like overlay analysis with the help of vector-based tools. Say, for example, here there is a like road network and there is a country boundary, and I want to like extract road network of this particular like country, and using clip function you can extract the road layer for your country of interest or your polygon of interest. GIS also offer many vector-based spatial statistics tools which offer methods for analyzing spatial distributions, patterns, process, and relationship. And these tools incorporate the spatial information such as proximity, area, connectivity, and other spatial relationship with statistics and mathematics. So rather than perform statistics and mathematics with the help of tabulated information, here you are defining or you are restricting your information based on the spatial location or spatial relationship so that you can combine many information, many sources of information spatially, and you can apply a set of spatial operators and you can extract meaningful information. One of the powerful analysis with spatial statistics is the spatial autocorrelation, which measures the patterns of attribute values associated with geographical space. It is basically works on two fundamental principles that are the distance and neighborhood, and using which you can able to identify the clusters, the outliers, the positive trend areas, the negative trend areas, the patterns, and so on and so forth. And all required our uh, what you call the neighborhood information, how we are considering the neighbor for the statistics. Either you can use the inverse distance function based on distance, you can define your neighbors, or using a fixed radial distance, you can decide your neighbors, or even zone of difference, zone of indifference of both inverse distance and distance band also we can put together and you can analyze the neighborhood relationship. Adjacency also used in addition to distance, and sometimes adjacency alone will be used to determine your neighbors based on specified number of neighbors surrounding your point of interest or feature of interest, or you can consider based on contiguity of your data, or even you can employ some special kind of spatial weights, and based on that you can decide your neighbors. So once you decided your neighbor and you can able to correlate the data values between the point of interest and neighbor, and accordingly you can create interesting statistical information that we call as spatial autocorrelation. Here so we employed a spatial autocorrelation, especially the Moran's high value, to identify the malaria hotspot case locations. On the left side, if you look at, you will find the average parasite index, which is nothing but the number of people chances to get malaria, number of thousand people chances to get malaria. And if you look at the western border of the state, have more number of cases, malaria cases, and most of the locations have a higher API values, which means the chances of getting malaria is high. But I want to share this information statistically, for which you can apply the spatial autocorrelation methods, where it consider one location and surrounding locations, and this location surrounding locations all have high number of cases and will be considered as a hotspot, and this location and surrounding locations all have low number of cases and will be considered as a cold spot. So you have two extreme clusters. One is the hotspot, positive values, and another one is cold spot, the negative value. In between, there are transition zones where statistically it's not significant, but still it may go to cold spot or hotspot. Now, through this statistics, you can establish a concrete inferences, and you can recommend a policy option, and you can infer some other attributes as well. If you look at this data set and all the elevated portions where the elevation is high, this color, this dark brown color represents a higher elevation. The elevations are high, the cases are very low, and elevations are less, especially the green color, the cases are very high, which means the cases are much associated with the elevation. And of course, elevation is also associated with forest, rainfall, and other environmental variables, and even sometimes variables with the population and socioeconomic characteristics. So simply with the case distribution or like a clusters, we can able to infer many information or many facts for which the spatial statistics are widely used, especially disease epidemiology, hazards, and other day-to-day problems. Similar to spatial autocorrelation, there are tools for analyzing patterns, analyzing geographic distribution, and even you can do spatial regressions. So based on release square and many spatial regression methods. And those are all very powerful, unlike the traditional regression analysis. This will compare based on the spatial relationship so that you will get very important insights. And GIS also offer tools to measure the distance very powerfully, and the distance can be measured in a radial manner. From a point, you can measure radius, and you can measure the a distance. But in reality, if you are moving from one point to another point, you should not measure the radial distance or direct distance. Rather, you have to measure distance in terms of network. So with that phenomena or concept, we can do many network-based analysis such as routing, service area, closest facility, origin, destination, cost matrix, vehicle routing problems, location allocation, and so on and so forth. And many real-world applications are based on this network analysis tools. So, for example, almost 15 years back, I did one analysis for a city in India, where I would like to understand how best the fire service stations cover the city, especially during emergency management. So when I compute distance with the help of a buffer tool or radial distance, it looks the three fire stations located in the city covers the entire city within 10 minutes of drive. But when I consider based on the network, it really not, because some of the networks are very poor, maybe have a limited speed limit, or some of the network may be very congested, and some of the network may not connected properly. You have to do a long routing. So if you consider all this joining of network and its characteristics, and if you calculate the distance or drive time zones, and you can able to understand very clearly how much area can be covered within set of specified minutes. So when I look at most of the peripheral areas not covered, and when I look at fire incidents, and most of the fire cases are recorded these areas, especially the satellite town, which gets fire service from the city center, and the traffic hinders like anything. So based on these analytical information, I proposed the establishment of three more fire stations to cover the city in a better manner. And after that, I have run again the new service area based on establish of new fire stations, and found that within 10 minutes of drive time, you can able to cover the entire city. Like you can optimize the resource, or you can do a better planning with the help of this kind of network-based tools. Even you can use these tools, especially location allocation tools, to identify the best location to start a new business. And nowadays, many business establishing their branches franchise based on this kind of scientific analysis. Say, for example, these are all the existing supermarkets, and new supermarkets can be located here and here based on the consumer availability or consumers' locations and their choice of preference. So you can identify the locations that capture most demand from the overall market area. As I told, you can convert your vector data into raster data or from discrete information to continuous information using interpolation tool. You can say, for example, with the help of elevation data, elevation point data, you can create elevation surface. Say, for example, here the ozone is measured using set of instruments at specified location, but some other locations don't have the ozone monitoring stations, but still you can able to estimate based on the interpolated surface using the known values. You can interpolate or you can extrapolate the unknown locations as well. Even you can do very modeling and scripting with the help of vector-based tools, especially for suitability analysis, where you have to consider multiple dimension and multiple data sets together in a very complex and logical manner, where you can put all together the multi geoprocessing tools, and where some output of certain tools may act as an input to another tool. So like you can take output of one tool and that become input to another tool, using which you can like integrate and you can develop a model and you can get a final output for suitability and other analysis. With this, I just stop it about the theoretical aspect of vector-based spatial analysis. Now I'd like to give you a short demonstration about what we discussed. Here, if you look at, you have, or I'm showing you like a region with some states, and the other layer is available, and this layer shows the towns in entire country. But I want to extract only the towns which is very relevant to this area, which means I want to clip only this part, the towns. So I can like use the geoprocessing tools available in our GIS. I'm showing you the GIS Pro. Say for example, you can open the geoprocessing of a clip tool. You can give your data, what data you want to extract. You want to extract the major towns uh, for a particular area. The clip feature is peninsular India, and you can define it. So where you want to store your data. So you can choose your like data. Say for example, like I just define clip towns, and I'm just like running. Now you have a new output which is only representing the towns within your area of interest. Okay. It's very within fraction of second it clips based on the spatial relationship between two layers, and using which you can do further analysis. So here with these two layers, I want to identify the inaccessible area, which means some of the areas may have a better service, which means which is well connected, and some of the area not connected well with the rest of the world. So in order to establish a new routing and new like connectivity, and I want to do some analysis where the inaccessibility is more, especially in which state the inaccessibility is more. By looking your the location of towns, you can able to see the bottom part of this area have a better connection than the like uh, upper part, upper counterpart. But again, within upper counterpart, which area we have to focus more, and I want to like look at. So for which I want to do some kind of analysis based on this vector data. In addition to the town location, I also want to use the major like a road network, existing road network, as well as existing the railway network, the existing railway network and the existing road network. So I want to do an analysis based on buffer because surrounding each city you will find a better connectivity. So I want to make it a buffer. So I can go ahead with, yeah, proximity analysis. Say for example buffer. First I want to create a buffer for the towns. So I just like define the distance. So I want to do it uh, maybe 30 kilometer surrounding a town have a better connectivity. Like I am assuming, and I can like run it, and you can able to get it. See now, these all like blue circled areas have a better connectivity with the rest, rest of the world, and whereas the area which are all wide have like a more inaccessibility scenario. But in addition, I want to add the similar approach for railway network and road also. Well, look at railway network available for the entire country, but I want to extract railway network only for this area. There are two options. Either you can clip it as like what you did for, or what I did for the towns, or you can do, yeah, yeah, what you call a spatial selection. Okay, so you can select the like a railway network. So based on say for based on your spatial like a query, okay, and like applying a spatial query called intersect. So whatever railway network which is intersecting with the background like a steady area, that is peninsular India, I want to select it. So now see, so all the like a network which is intersecting with the background area is selected. So only for the selected area you can perform again the buffer. You can select your railway network. While selecting this data set, the system automatically detect some of the future, some of the records have been already selected, whether you want to run a buffer only for those like selected things. Yeah, you can do like buffer for this, what you call railway network, using maybe about a 10 kilometer distance for the railway, major railway roads, and you can execute it. It will take some time because the number of like records are more. It is about 22,000 plus number of records, so it will take some time. But in order to reduce the time taking process, I just already I buffered, and I like shown you. See, this is the selected the railway network, and this is the buffer which created around the selected railway network. Likewise, I want to do, yeah, like buffer for road network as well. Again, you can do it. Now this time instead of railway network, you can choose the road layer, and again you can apply the similar like concept, which means the road layer intersecting with the peninsular polygons, and you can apply what you call intersection. Even sometimes you can add further like criteria like search distance around your intersection feature also you can do it. And now see all road network related to or relevant to this like a steady area have been selected, and again using which you can do, see, using which you can do further like a buffer analysis. This is also I already ran, and I added the results here. Now see, you have three buffers. So one is buffer based on your towns, another one is buffer based on road network, another one is buffer based on your railway network. And there are areas which is not covered all these buffers, so those areas we call it as inaccessible areas. It's not like connected, well connected with the rest of the world, so I consider these areas as inaccessible area. But I want to like calculate the total area and in which like a state it is high, and I want to consider with the population and other like attributes also. So I want to extract as a separate layer, for which I want to integrate all these layers together, which means all these buffers together, for which you can use the tools called overlay tools. I'm just adding like the layers together. Say, for example, I am adding the buffer of towns and buffer of railway road and buffer of road, and you can define okay, so where you want to set it. So once you've done and run analysis, you will get a new layer that is called you can call it as the buffer of all. See, now all the buffers are integrated together using a geoprocessing tool called union, and that is like as a single layer, that is created as a single layer, and using which I want to compare it with the background like a steady area, and I want to extract all inaccessible areas as separate. So for which you can use a feature called the clip. Okay, so I can clip the steady area peninsular India with the features of your railroad and town buffers, and you can like run it. The moment you run, you will get area, and that area it's called like inaccessible area. So if you look at on all this like dark orange color represents the inaccessible area, and you can see, and this inaccessible area is very high in these states Maharashtra and Andhra Pradesh, and you can look at its attribute, where the inaccessible area is high. See, in this state it is very high, the inaccessible area is high. Next to that, this state, the inaccessible area is very high. And how much area and what is the population, total population of these areas, and based on that you can establish some like spatial planning and other measures. I hope you understand that the powerfulness of vector-based analysis using geoprocessing tools. And thanks for listening.